Lecture 7. We're going back to the idea of atomic structure, but now we're set. Now we know the nuclear model of the atom is the way to go. We've identified all of the particles in the atom. Now we're going to look more specifically at their properties, how to count them based on information on the periodic table, and what's up with isotopes. What's up with the change in the number of neutrons and what it does to the atom because the neutron has mass. For your chart, for both the proton and the neutron, we find them in the nucleus. That was specified, the proton was specified by Rutherford, and once the neutron was found by Chadwick, we realized it's in the nucleus also. And the electron orbits the nucleus. It's not inside the nucleus, it's traveling through the empty space that makes up the rest of the atom. The charge on these, now there's the fancy one, the Coulomb's one that we talked about, and what's cool is where we learned that the electron is negative 1.602 times 10 to the negative 19th. Coulombs, I know I ran out of room, I'll make it better. For my electron, my positive proton is exactly the same charge, 10 to the negative 19th, but positive. So protons and electrons exactly offset in terms of charge, and neutron, no charge. To make this easier, we count the proton as a 1 plus charge, and the electron as a 1 minus charge. Those are the ones I expect you to remember because we compare them to each other, positive versus negative. When we write these charges, we write them following the number. Do I really care if you write +1 for your charge of neutron or for your charge of proton? No. This is the convention to write them after. It's better, but I'll definitely still take it the other way. For symbols, this is why I said it wouldn't matter with our spacing. What I want to do with symbols, P with a plus sign for proton, N with a 0. That's not a degree sign, that's none, like no charge for neutron. And electron, I already showed you with the negative. I use those all the time. I do not write things out. For my mass in grams, I'll tell you that the mass in AMU, atomic mass units, is much more important at 1, 1, and 0. But the mass, we already talked here, is 9.10 times 10 to the, see it is 9.11 also. It's negative 28 grams, oh so tiny. You're going to get a little more mass to the proton and the neutron. 1.67 times 10 to the, oh, it's still ridiculously small, negative 24th grams, and that's going to be my neutron also. Protons and neutrons at negative 24, we count them as having mass, even as tiny as they are, but when you get to the negative 28th of the electron, we say no. Again, I care more about your masses in AMU, atomic mass units, knowing proton and neutron are 1 and electron is so small we count it as 0. When we count subatomic particles from the periodic table, we're going to use both the atomic number and the mass number on the periodic table for those. Remember, your atomic number is the number where an element is found. Hydrogen's 1, helium's 2, lithium's 3, beryllium's 4. Your mass number is the decimal number of the mass, rounded. Hydrogen 1.0079, it's 1. Lithium 6.941, it's 7. You round to the nearest whole number for those. So my atomic number, the whole number, atomic number equals number of protons. And my mass number, these are in your notes, and that's why I'm just writing out the quick version. Your mass number is going to be your number of protons plus your number of neutrons, because those contribute to the mass of the atom. Those are the particles that have mass, so those add up to the mass number. My number of protons, remember, is going to be my atomic number. Number of protons, the reason I have it written there, make sure that you know that it identifies an atom. So every time I have nitrogen, it's 7 protons. Every time I have neon, it's 10 protons. Every time I have, what else is on there? It's on the wall behind the computer. 43 protons, technetium. Always, always, always. Neutrons and electrons can change. Speaking of changing my number of electrons, my number of electrons in a neutral atom. One with no charge, number of electrons equals atomic number. Atomic number. Again, so in a neutral atom, it makes sense protons equal electrons. With their offsetting charges exactly equal but opposite, this will give you an atom with no charge. If you get 2 bonus points on a test and have missed 2, positive and negative exactly offsets. Good. So for cations and anions, though, we need to make a small change in our count. Remember, cations are positive, so you'd have something like aluminum plus 3 plus to write it best. When I have this means that I've got 3 more protons than electrons, 3 uncanceled protons. So for my atomic number there, for cations, I'm going to subtract 1 electron per positive. And for anions, like sulfur with a 2- charge, I'm going to add 1 electron per negative. There you go. So my number of neutrons, again, is going to be mass number for neutrons, mass number minus atomic number. Up here I said protons and neutrons made mass number. Mass number minus atomic number goes back and gives me number of neutrons. Put your atomic symbol there so you could check it out with mass number and atomic number. So let's look at some of these practice questions. How many protons, neutrons, and electrons are in iron? Going once, going twice. Iron, Fe. Number 26 on the periodic table with a mass of, I believe it's 56. Let's double check. Mass number of 56 for my mass number. There's no charge on iron, so protons is going to be 26. And that means electrons is 26 also because I don't have a charge. For neutrons, mass number minus atomic number for 30. Give atomic number, mass number, and numbers of protons, neutrons, and electrons for 81 Br. If you look at the symbol above, that 81 is my mass number. I find bromine on the periodic table at number 35. So I do the same for bromine. I've got number 35 and a mass of 81. 35 protons, 35 electrons. 81 minus 35 gives me 46 neutrons. Good. Complete atomic symbol for the element with 31 protons, 40 neutrons, 31 electrons. 31 protons means it's number 31 on the periodic table, so it's gallium. 31 protons, 31 electrons means I don't have a positive or negative charge on it. The complete atomic symbol includes my atomic number here at the bottom and my mass number at the top. Mass number is protons plus neutrons, 31 plus 40 for 71. There you go. Atomic mass and atomic weight gets picky. Atomic mass is the mass of one atom, and it's basically your mass on the periodic table reported in AMU. It's based on the idea that smaller masses are better when you're talking about a single atom, and then you don't have to use 10 to the negative 20 whatever grams. You'll also see it as A. 1 AMU, and you probably want to look this up. I will read this, though. 1 AMU equals, it's like 1.66 times 10 to the negative 24th grams. 1.66 times 10 to the negative 24th grams, but this is important. 1 gram equals 6.02 times 10 to the 23rd AMU. Like a mole of something, like a mole of atoms, make up a gram. That's where we got it. It has to do with the relationship between the mole and the mass on the periodic table. The element used to standardize this was carbon. And basically, how this made getting atomic mass is simple. is it's set up so that the mass on your periodic table, you can write whatever you want in your packet, the mass on your periodic table in grams is your molar mass, and if you give it an AMU, it's your atomic mass, the mass of one atom. So using the relationship between moles and grams, standardize that mass that's on the periodic table. Do I care if you remember that? No. Do I care that if you put grams on it, it's a molar mass, and AMU makes it an atomic mass? Yes. So for isotopes, the average atomic mass, or the average weight of that's given on the periodic table, is a decimal, because the differences in numbers of neutrons among isotopes give me different masses. I'm going to do this pretty quick. So an isotope, the atomic weight is the mass including percentage of isotopes, and we're about to look at that. What an isotope is the same type of atom, but with a different number of neutrons and then a different mass. If you look at a sample of an element, the relative abundance is how much is composed of each isotope. So it might be 50% of one and 50% of another. If you make it as a decimal, it's the fractional isotope abundance. Let's check out this problem, and it'll show you how you get the mass of magnesium. If I ask you for its mass number, you'd tell me 24, but if you look on the periodic table, it's 24.305. Here's how. 3 magnesium isotopes have atomic masses and relative abundances given. Calculate your atomic weight of magnesium. All you do is the mass that's given times the percent as a decimal and add them up. 24.986 was my second possible mass, and these are all in AMUs. I'm just not writing it yet for spacing, and that's 0.100. And we'll add on my third option here, 25.982. Very small amount for this one again, 0.1101. Those are my masses, and my percents turned to decimals. Please do this calculation. Take a second. If I do this, I come up with 24.305 AMU for my mass of magnesium, which is what the periodic table said. What would be different among these isotopes would be a different number of neutrons, which would be a different mass of those isotopes, because neutrons have mass. This is the percent of a sample that is each of these isotopes, so you multiply the mass by how much you have of it, and add it up to a total, like calculating a weighted grade. There we go. Got that all out. Isotopes can be confusing. Try your practice problems and check out your answers.